So, the title of my talk is Patterns for Cognitive Systems. We're going to do an introduction, show the method, and then just review the different patterns. So, by cognitive system, what do we mean by cognitive system? A cognitive system generally refers to anything, all intelligent systems, including cognitive architectures, robot control systems, intelligent agents, anything that's able to receive sensory stimuli from the environment, arrive at some conclusions, and recommend or pursue a course of action. So that's a general term for cognitive system. And a couple of years ago, I was trying to build one. And so I really wanted to understand, well, how did other people build their cognitive systems? Because I had some idea, but wasn't quite sure. So I did a survey and looked at a number of cognitive systems across many domains, ranging from robotics to question answering. And the main objective of the survey was to understand how these different system architects integrated four tasks: perceiving stimuli from the external environment, being reminded of past episodes, planning actions, and then acting upon the environment. So those are the four areas that were of interest. And so in conducting the survey, I came upon a number of patterns which I think will be useful for people in the future. So we reviewed 24 cognitive systems, more or less, actually a few more than that. Each system had a system architecture diagram which depicted the major components of the system, typically a data flow diagram. In most cases, the sensors and actuators of the system were in different places on the diagrams, and often similar components had different names. So it was hard to compare the diagrams because the orientation was off, or the diagrams were just labeled different labels for the same item. So, for example, a sensor component in one diagram was called a monitor or a detector in another diagram. So, essentially, to identify and to canonicalize these diagrams, I came up with a template, and in order to align the diagrams, we've made several regions in the template for the various areas of perceiving, reminding, planning, acting, and control. And so all the diagrams we then retrofit into this template so that we would be able to compare them. And so basically on the diagram we have a body, which could be a robot body or a graphical user interface web browser, which interacts with the world, whether the world is virtual or real world. And then we call this the body, and then we have the mind, or the cognitive system itself, and there are areas where perception happens, where reminding happens, where planning happens, and where acting happens, and then there's some control that coordinates these various activities. So some sample systems, simple and complex systems that we looked at. Simple system would be one by Yannis Demaris and Matthew Johnson, which was for action recognition and imitation. This was represented, basically they had a perception component, they had a representation and classification component, and an action component. A more complex system that we looked at was the NASA Telerobot Control System, NASRAM, which was used in undersea exploration and controlling autonomous vehicles and so forth. So that had a little bit more complex, layered definition, and where you have multiple layers of sensors, models, and planners that looked at distances that are very close, ranging out to distances that are very far. So this is a list of the different systems that were looked at. We looked at Actor, some very classical systems. Actor, case-based planner by Hammond, SOAR, Daydreamer, which is a system for doing daydreaming. Watson, IBM Watson, we looked at as well. And then I also, number 14 is the system that I'm working on, which is PAM P2, means Position Autonomous Modeler. And the goal of that system is to build up its own internal ontology, its own internal representation of the world by its interaction with the world. So the patterns we discovered were observation, coordination, reminding, reaction loop, deliberation loop, reflection loop, motivation, simulation, regulation, and compensation. And just as a summary, the various systems, most of the systems had some of these patterns in them. None of them had all the patterns, not even the system I'm designing, which is basically a unifying many of the patterns. But many of them, have strengths in different areas, as outlined by the patterns that they exhibit. So the patterns. So in general, I'm just going to show this specific presentation. It gives a synopsis of the pattern, the elements that are in the pattern, and the forces, the reasons why you want to use this particular pattern. And here we have a simple mind-body pattern as a sample, where you have a body of the system which has sensors, which take information, take stimuli from the external world. You have monitors which look internally at the body and will present stimuli to perception, but it's internal as opposed to external. And then you have actuators which act upon the world and then give some kind of result as to the state of the action that had been taken, as to whether or not the action succeeded. So, for example, if you have a robot arm that is attempting to move forward, you send a signal from the executor to move the arm, but it's blocked by something, then you have a failure because the arm couldn't extend as was desired. So pattern number 1 is observation. So the observation pattern essentially saves the perceptual stimuli that came in from the sensors. And you'd want to use this pattern when the cognitive system needs to share perceptual information with multiple internal components, or when you want to record a historical trace of the sensory stimuli that it has encountered. And so we see here, we see here that the body is receiving stimuli from all the sensors, and even the body could be a room, which takes in information from various situated sensors. And the sensors go into some perception module, and the perception module saves or persists in a cache or in a database, for example. So this is the observation pattern. So this is the Piaget autonomous modeler, the PAM P2 system, and it has about 27 components or so. And these components are used to implement various patterns. And right now, for observation, the components that are involved are basically the perceiver, the current viewpoint. Viewpoint means context or state, and then monads. Monads is our representation for a proposition. So just a simple proposition like R over M1, M2, M3, we represent as kind of like a neural proposition where we have our terms on the bottom, M1, M2, M3. We have the relationship R, and then the reifier or the definition M. So the circles are entities or constants, and the body of the box represents proposition. So second pattern is coordination. And so coordination is essentially inferencing. When you have additional inferences that you would like to add to your current state. So first, initially, you get the sensory stimuli in, but then you may want to generalize on that stimuli or infer certain things. So coordination is the name of the pattern that you use to add additional inferences to it. And the coordination pattern is helpful when you have the cognitive system needs to leverage abstractions or generalizations in addition to the raw sensory stimuli in its reasoning process. Oops. And we can see how this works. So the body is sending stimuli to the perception module saving the stimuli into the current model of the world, and then we have other components, maybe a correlator, which does some correlation between the current state and a predicted state or expected state, a reasoner, which adds more information, maybe a predictor, which is going to generate new predictions based on the current state. Maybe you have a planner that is acting on building a plan of action based on the current model, or some other kind of inferencing. So in the PAM system, PAM-P2 system, we have these entities, these components as implementing the coordination pattern. So the blue areas indicate data stores or data services, and the yellow and the pinkish components are processors. So they're either saving data to the data service or retrieving data from data services. The third pattern is reminding. So the reminding pattern basically uses episodic memory to retrieve candidate episodes for use by some kind of evaluator. And so the perception provides stimuli to an action selector, and as well the actions are used by the episodic memory to form episodes. So the reminding pattern is useful when it's necessary for the cognitive system to consult a historical record of actions undertaken, and it's also useful for establishing pre-programmed responses to specific situations. And so we can see, the body receives information from perception. Actions that are decided to be taken are stored in the episodic memory, and then later retrieved by the retriever. And in the PAM-P2 system, the perceiver generates a current state, which is saved into the propositional monad repository. Then associators are used to store these propositions into the scheme memory, and then they're retrieved where they can be retrieved later. And we have two kinds of action selectors. We have a deliberator, which works with plans, and a reactor, which works with reflexes and habits. The next pattern is reaction loop. And in reaction loop, basically we have a body which is selecting reflexes to be executed. And the reflexes are fixed, pre-programmed responses to specific contexts or specific sets of stimuli. So essentially, the action selector pulls in reflexes and pulls in the current context, current state from perception, and then indicates to the executor what needs to be done. And in PAM-P2, we have methods which represent reflexes, habits, and plans, and the reactor sends the information to the user. There's another variant of the reaction loop, which is called the acquired reaction loop. The first one was an innate reaction loop, and acquired reaction loop, the difference is that we may employ goals, and the habits are stored back into a library. So, whereas before we had just a fixed set of reflexes, here you can actually store the actions that are undertaken as habits. We have a deliberation loop pattern, and the deliberation loop, basically perception feeds a planner, and then the planner looks at actions or plans it may have already and goals of the system, and then basically chooses the appropriate plan or action to be undertaken. And when you need a proper sequencing of available actions, that's basically when you use the deliberation loop pattern. And we can see here, this is pretty much the planners pulling and storing plans and pulling goals, all based on the perception. And in the PAM-P2 system, basically our action selector, we have a planner and we have an action selector. And the current state comes in from the monads, or the propositions, and the planner will look at the agenda, which is our goal set, and devise a plan to achieve the goals based on the current state, but it will save the plan in the repository, and the deliberator at some point will look up the available plans, and it may find that plan is relevant and pull that one, or it may find a different plan is relevant if the goals have changed and pull that. So we don't have the planner, actually sending information through. We have a deliberator, which basically looks at the goals, looks at the current state, looks at the available methods, and then selects one. And then we also have an action inhibitor, which is sometimes we don't want to deliberate, we just want to daydream. And so if the action inhibitor says go ahead and do an action, we will, and if not, then it will just execute. And so there's also a hybrid deliberation loop, and basically in a hybrid we're doing reflexes and we're doing deliberation at the same time. So if there's something that happens that you need urgent attention to, it will do that through the local action selector. Otherwise, it will deliberate and plan. So you can have reflexes override plans that you've constructed. And in PAM, we do have this hybrid two paths essentially going through. We have a reactor and a deliberator. Reflection loop. Basically, reflection is whenever you need to throttle components or you need to increase and decrease the throughput of the components. So via reflection, a monitor process monitors all the components in the system, and then a modifier will change the components. Maybe it'll turn some off, maybe it'll turn it on, maybe it'll allocate more as necessary. So that's reflection. And for basically, the sense is that the monitor and the modifiers are reflected upon the operation of the system and acting accordingly. And in PAM, we actually don't, in PAM-P2, we don't implement any reflection. Motivation is when motivation pattern selects and prioritizes goals based on the perceptions and needs of the system. So needs are monitored, emerge from the monitors, and urges, which is the delta between a target value for a need and the actual value. So you have a homeostatic value, maybe temperature, and there's an ideal value for the temperature, which may be 25 degrees Celsius. And if you have a change in the temperature, this generates a delta. And so the greater the change is, the greater your urge to fix it or to correct the situation. And so, or water need, maybe thirst or energy level or fatigue, and so on. So basically, this pattern, the urges come in from perception to the attention module, and the attention will reprioritize the goals of the system. So if you're thirsty, then you want to get water, or if you are low on energy and you're a robot, you want to plug in and recharge yourself. So your goals will be shifted to get the most important goals, and then the action selector will look at the reprioritized goals and choose the appropriate action. So, just a little simulation. So basically you have needs that are pre-programmed into the system. You have actions, you have goals that feed into the attention system. The attention component will reprioritize the goals as needed based on the urges, and then action selector will choose the appropriate actions based on the reprioritized goals. And we have in the PAM P2 system, we have an attention component, we have correlators, and the agenda is modified by the attention system. Simulation, this is mental simulation. The reason you would use simulation is when you want to consider the possible effects of a plan. So this is kind of like daydreaming. When you want to see what the possible effects of a series of actions might be before you actually perform the actions. So with this, you apply operators to a forward model and to predict what the future states will be. And then at some point we have a supervisor component that says, okay, it's time to stop daydreaming, it's time to really act upon the world. And basically what happens with simulation is that you will act upon the world for a period of time, then you will stop acting, your actions will be inhibited. And then you will take some mental actions. You will take some mental actions and adjust your forward model of the world, and then that feeds back into your perception, and then you will build up a forward model of what a scenario that you think will happen, and then eventually you will come and you'll execute your actions. So that's simulation. And in PAM system, simulation supervisor and the action inhibitor are what govern the simulation. Last, pattern number 9 is regulation. And in regulation, we want to modify the system's behavior over time using feedback from the environment, from what you predicted would happen to what actually happened. When you take an action and you think that, and the action produces the desired results, then you want to reward or reinforce that action. When you take an action and it produces unexpected results or undesirable results, then you want to correct that action in some way. So the regulator component here is what's used to modify the actions. And modifications could be deleting an action. Modification could be increasing the salience or importance of the action. It's up to the implementer actually to determine how to reward or correct actions in the system. And we have a regulator component which does just that. Finally, compensation is enabling the system to achieve reversibility. This is something that a few systems have, but it's not really, it's affecting a repair. So for example, if you take an action and your action doesn't achieve a goal, but it puts you in a state that is kind of unworkable, then you want to do either one of two things. You want to reverse what you did, or you want to neutralize the effects of the state of the current, the new situation. So compensation will reverse the actions, or it'll create actions which are opposite to what the steps you've taken, or it will change the goals so that you can it'll change the goals so that you can have new goals to correct you and maybe get you back to your initial state or a different state without the deleterious effects. So basically that's compensation. And there's a compensator component which provides compensation, which performs the compensation. And finally, we have another pattern, which is basically, once you build your cognitive system, you need some way to run it. You need to connect it to the real world. And so what we propose to do is to build a mind server so that I can create an instance of my mind and have it connected to a device or a robot, and or allow other developers to construct their own minds. And the person on the mobile phone can say, okay, I want to choose this particular type or another type for testing, but basically have minds provisioned dynamically in the cloud and have the devices run and use the cognitive systems directly. So I just want to give thanks to people who have helped me along the way and who I'm working with to produce these systems, and definitely look for more collaboration. Always looking for collaboration. And just want to know if you have any questions.
Okay.